Dr. Xu is received his PhD from Western in 2004. After that, he was appointed assistant professor in Lakehead University, and later on promoted to associate professor, all in chemical engineering department. And now, since 2011, he moved to Western University as an INSERC, Industrial Research Chair in Forest Biorefinery. And he's currently leading the Industrial Bioproduct Laboratory founded by CFI. Dr. Xu has been very successful in his field of research during the past almost 10 years. He received the prestigious award from Japan Institute of Energy Outstanding Young Scientist Award in 1999. Last year, he received the prestigious Synchro Canada Innovation Award by the Canadian Society of Chemical Engineering. Anyway, he has published a lot of papers, over 100, and today we are honored to have him here to introduce his research. And after the presentation, feel free to talk to him. I cannot introduce you individually. I hope you have a chance to talk to him. Okay. Now, give it to you, Dr.
Thank you, Charles. So really, my pleasure to be here. Actually, it's a kind of the friendship because Charles is my friend, and I know him from actually 5 years ago when he's still working in Calgary. So and recently we have more discussion about the future collaboration in the area of bioenergy, and this could be one opportunity we can have the first step to establish some potential application here. Because my research mainly is on the forest biorefinery. It's kind of the research now is a little bit hot because the biorefinery is looking at a more value-added product, chemical and materials product from the biomass. So I hope that we can get some of interaction more in the future through the research and also through the student co-supervision. Actually, we already started one co-supervision student, and the PhD student already started in just 2 months ago. So it's kind of a good start. So, and also the second reason I really want to have this chance to visit here is because I like the name WISE. It's really a good name. So hopefully here we got lots of new ideas, some of more interaction with the industry, get some of the new product to look at. So in terms of research and education and student training. So here is my topic here today is a thermochemical and catalytical upgrading of biomass into industrial bioproduct. So this is regarding the upgrading, so conversion. So we included several of the sample, not sample, showcase of my research. But before that, I just want to quickly go over what's the background, what's the motivation, what's the potential for the biomass. Here is my institute. We call it ICFAR. So similar as we pronounce as the IC seems like the IC far away. So that's the good manners were embedded with this name. It's located off campus. Actually, it's established in 2009 with a significant amount of funding from the Ontario Research Fund. So it's about $5 million to establish this research institute. It's a physical institute. It's a building off campus. So I accommodated 3 professors, including myself and my 2 colleagues, and they're working on the pyrolysis, gasification, some activities also in the chemical engineering department and mechanical engineering department here, similar activities. And some of the picture here, that's the institute. So it's a new institute for the chemical institute for chemical fuels and the chemical fields from alternative resources. We call it ICFAR here. So it belongs to Faculty of Engineering in Western University. So some of the research facility here, that's the big reactor. It's a fluid accelerator reactor. It's a parallel scale reactor. So for biomass conversion and also for the oil sand, the tar sand conversion, tar sand upgrading. And this is also the short reactor here. That's the model developed by the institute working on the biomass pyrolysis. This is a mobile system. It's kind of gained a reputation because this mobile system is only one maybe called a mobile system in Canada. So it's kind of the new technology which can be applicable, particularly for some farms, some remote area. They want to have some biomass conversion to get some energy, get some fuels from biomass. So this could be a very suitable application. And then a spin-off company already created to commercialize this technology. Okay, so just a brief overview about what we are talking about. It's the industrial byproduct. So looking at industrial byproduct, simply, the definition is simple. It's just any product, is any chemical and material product derived from biomass. We can call it industrial byproduct. Looking at biomass, actually, there's some background. We know that we are nowadays facing as challenges. It's the fossil fuel, the depletion of fossil fuel, and the environmental issue, air pollution, water pollution. So those are related to why we should look at the biomass. Biomass is include a wide variety of living plants and animals. So those can be a biomass. So we look at any biomass related product. So we can look at a particular chemical and materials. And the question is why we should look at a chemical and materials only, not particularly focus on energy. So energy is very broad. Energy can be anything. We can look at electricity. Can be any energy form. Some different type of form of energy. But chemicals are also related to energy. So without energy, we cannot get a chemical. Energy can be used for chemical production, and the chemical production related to energy. So those are the questions. So why we particularly look at the chemical and the materials, not too much focus on fuels. This is a good lesson we can learn from the petroleum industry. We know that petroleum is mainly for the different. We rely on the petroleum because we need to get fuels, transportation fuels, and also we need to get some of the chemicals. For example, polymer. And we get some any type of the materials related to chemical. So this is petroleum consumption. We have 4% of consumption of petroleum for the chemical only, compared to 70% of the petroleum is currently used for fuel generation, particularly transportation fuel. But on the other hand, look at the revenue. So the chemical revenue is $375 billion, the worldwide, and the fuel the revenue is similar, 385. But the consumption, the feedstock, consume too much feedstock, which give the messages that the fuel is cheaper. Chemical is much more expensive. So if you look more on fuels, then maybe the economic aspect is less attractive compared to chemicals. So that's the take-home messages. Chemicals are more expensive than fuels. So we should look more on chemicals, particularly for biomass. Biomass is kind of the materials very useful for chemical, not too much for fuels. Probably that message will have some different understanding. And here is kind of the summary here. It's the market share of industrial bioproduct in the US. So we can look at the different industrial bioproduct: adhesive, fatty acids, surfactant, and say some materials, active carbon, plasticizer. It's kind of chemicals from the biomaterials. And also we have some dyes and paint, ink, plastic. So those are here's the total production, million tons. And the other column show the percentage from the renewable resources. For example, 40% means 40% of adhesives now currently come from renewable resources, from plants, which is not bad. And for some of the performance is not that good. For example, the plasticizer, only 15% come from biomass. And the majority, 85%, come from petroleum. We know that from petroleum. So those are the performance. So that's the ratio of the renewable component. So we have significant amount of room to improve. The idea is that we can increase that to 80% or 70% at least. So which means that we can produce more chemicals from renewable resources. That is biomass. This cannot be replaced by we're not talking about energy, renewable energy. Some of you may think about it, we can get a nuclear energy, say. Nuclear energy really could be the future for the energy because it can generate electricity, and electricity can be used for transportation, say the electrical car and for other purpose. But in terms of chemical, we cannot get a chemical from nuclear energy. So you must get something to produce chemicals. So that's the reason make the biomass more important, not only for energy, but for chemicals. So that's the message here. So for chemical production, we can produce more chemical from renewable sources, particularly biomass. And how about the money-wise? The money-wise, the economic-wise, the market outlook. So we can look at it in 2015, which is not too far from now, only about 2-3 years only. And there's about $200 billion world market. That's a big number. So look at how the breakdown. So 62 billion of the market could be the green chemicals and alcohols, particularly for the fuels. Alcohols can be for the chemical feedstock. And bioplastic, resin, platform chemicals. So those, if summarized together, is about 200 billion. And also the growth rate is also so big, particularly for example, for the bioplastic, the resin, composite. This can grow very fast, 23% per year annual growth, which shows that the potential is very high. So we should look at more now at least to get more idea or get more technology developed to convert the biomass to chemicals, to industrial byproduct. And some summary here, particularly for the forestry industry, because we know that forestry in Canada is very important. It's related to 3% of GDP for the whole country. So it's important sectors in Canada, forestry. So there's a global biomarket opportunity, $300 billion. So this is market potential. And for green chemical would be the 62 billion. And for the forestry industry, so that's an opportunity. So Canadian forest industry is posed, okay, so it's positioned to be a dynamic contributor to the new bio age. So in Canada, we call it bioeconomy. So which is related to how we can more involve the biomass as the component for the economic development. That's the bioeconomy. And this is also show the growth of the renewable chemicals. So from today and 2020, about 10 years, and we can see the five-fold increase in the in the chemicals and materials demand, which is biochemicals derived from biomass. And another 30 years down the road, we can see another five-fold increase again. So the total, we can look at it in 2050, the market share of the biomaterials, biochemicals, could be similar as the supply from the fossil fuel, which is huge. So which means a 50% contribution can be achieved if you follow this the expectation. So that's the market. Then we should look back about the resources. Do we have enough resources to achieve that goal, to get more chemical from biomass? So that's another big question we should answer. So first look at the U.S. side, because our neighbor. So the U.S. about 1.3 billion metric ton of biomass, which is a large amount, 1.3 billion metric. And the breakdown shown here, about a third of them come from crop residue, corn stalk, wheat straw, rice straw. So those are the main contribution for those residues. And also there's another about 1/3 collectively, so we can add them together. That's related to forest. So forest, biomass, and the residue, we contribute another 1/3 of the contribution. And then energy crop, switch grass, something like that. So which have another contribution. So in total, 1.3 billion metric ton, which is very good enough. You can supply about a U.S. energy demand about 21%. And also 30% of the transportation fuel can be produced. So that's why the Obama government now is really focused on how to get some transportation fuels from the ethanol, butanol, or those of the LG. So those kind of the bio-based fuels. In Canada side, so we have about 23 million oven-dried biomass from agriculture sector, about 30 million tons. And also, there's significant amount of biomass in the forest. Canadian forest actually is a 400 million hectare forest. This is that's actually 10% of wood forest. So 10%, which is a very large portion. So the forests are located in Canada, so which can provide a significant amount of the biomass. The residue, forest residue, the sawdust, the bark, the harvesting residues, those can be utilized as the raw material for chemical and fuels. So this is a forest residue. So we did not have the actual number, but a significant large number, because look at the forest, the area. Okay, so now look back. So if you have the resources, we have the demand, then what about technology? How we can convert the biomass to chemical, to value-added byproduct? That's the question related to our engineering, science, researchers like us, and graduate students for future career. So that's related to how we can convert those resources to the value-added product. So if you want to convert the forest biomass, we just take this example, a piece of wood. A piece of wood like this contains 3 major components. So one major component is here, 35% roughly is cellulose. Cellulose, we are familiar with that because that's the world number 1 natural polymers. Because the poly is a polyglucan, so it's glucose linked together. It's a long chain polymers, and molecular weight is very large, can be more than 10,000 or 100,000. Okay, so that's the bigger polymers, and we can break down them by hydrolysis, either enzymatic or chemically. So we can get the glucose, and the glucose can be a platform of materials. We can produce chemicals. For example, we can do fermentation, get ethanol. We can get a fermentation, get a lactic acid. We can produce the PLA, the polymer. We can also convert the glucose to the HMF, which is the hydromethyl furfural. This HMF gain some interest, particularly for the fuel. We can get the furan, so we can get a dimethyl furan from this. So as a gasoline replacement, or we can produce many polymer from this HMF. So this actually is a research converted glucose to HMF as another hot spot in the chemical engineering, particularly in the fuel, in the in the green chemistry or bioenergy side. And another portion here, about 35%, is hemicellulose. Hemicellulose is a mixture of the glucose and xylose. It's a 5-carbon, particular 5-carbon the sugar. So this can be also fermented by using some of the yeast. We can fermentate to the ethanol, but we can easily convert the xylose to furfural. Furfural can also be a chemical because it's aldehyde, so we can get lots of the natural aldehyde by using furfural, and also some of the food industry they can use furfural. So here, the remaining 30% is a lignin. The lignin is of particular interest because lignin is a natural polymer of the phenols. And the phenol is one of the main industry chemicals. We need phenols because one of the simple applications, we need adhesives. Lots of for example, the wood, the furniture, the house in construction or desk, those wood is not original wood. Those are engineered wood. We need adhesive. We need for example, we produce this by particle board or the plywood. So we need to stick each other strongly. So that's the adhesive. Those main adhesive components are phenol formaldehyde resin. So we need to get a phenol to produce those resin and adhesive. But this is a natural phenol, so which make this main applications how to get biophenol from the lignin. Okay. So this part will be covered in the later talk about that one application, one research we are doing. And a biorefinery. So as Charles already introduced, I'm now looking after the industry research chair program in forest biorefinery. The idea of the biorefinery is really similar as the petroleum refinery. We produce the diesel oil, gasoline, lubricant, oil, or produce some of chemicals, coke, of liquid propane gas. Those actually are end product. Those end product may come from a petroleum by refinery, by separation, by the upgrading. But similar idea, biorefinery is we take the biomass to replace the petroleum, but our target is similar as we need to produce multiple products, including fuels, including power, electricity, biofuels, and some chemical like this. Just several examples here. And in terms of the technology, we can convert the biomass. We can convert the conversion the biologically or biochemically by the hydrolysis and fermentation. We can also convert the biomass more readily or more faster, okay, through the thermochemical way. So we can do the simply by combustion can produce power, okay, and we can do the gasification to produce syngas, then followed by the catalytic synthesis. For example, the Fischer-Tropsch reactions, or for example, the syngas to the methanol, syngas to ethanol, or the high alcohols. Those can convert the biofuel, okay, and also we can do the liquefaction. Liquefaction is another option we are looking at recently years. So we can directly liquefy the solid residue, solid biomass, to a fuel, to a liquid. This liquid we call a bio-crude oil. It's similar as a petroleum crude oil. Then we do the refinery. We do the upgrading, separation. We can get those chemicals. So that's a different technology. But today actually we are focused on thermochemical route because my expertise in thermochemical, not a biochemical. So that's the reason. So I want to highlight here. So we look at the thermochemical routes. And the biorefining technology, the platform. So we have different platforms. We know that we have biochemical platform from fermentation and those thermochemical platform. If you look at thermochemical, actually it's more popular. Even a biochemical platform, we have some of the overlap. So we have some of the, for example here, so I highlighted here. So some further processing can be thermochemical. Biochemical, so further processing can be thermochemical. So those make the thermochemical is very popular. Okay, no matter what process initially we can get a biological conversion, thermochemical conversion, but the final product, normally we will use the thermochemical. For example, catalytic upgrading, cracking, okay, synthesis, those are the thermochemicals. So here shows some of example, lignin, sugar, okay, protein, gasification, those are thermochemical, particular thermochemical. Okay, so from now and on is some of research, of my own research. Just want to showcase a couple of examples, 3 examples here. So based on the thermochemical and catalytic upgrading and biomass to industrial bioproduct. First example is regarding the starch. It's agricultural biomass. And the second example is a forest biomass. It's a production of biophenol and a green resin and adhesive from a forestry residue. And the third example is the agricultural or forestry biomass. It's a novel one-step catalytic process to produce one butanol and one hexanol from bioethanol. So this bioethanol can be derived from the corn, can be derived from the agricultural residue, can be derived from wood. So, but the downstream processing, we want to convert ethanol to butanol and hexanol, which is the more value-added product. So that's the one-step conversion. So I like to give that example as a thermochemical and a catalytic upgrading. Okay, so the starch. We know the starch is very popular because that's a food. Okay, so we get the potato, corn, those have the starch. And if we relate to the starch here, starch can be also not only for food, can be also used for plastic materials, composite materials. So that's the starch-based materials. That's the biodegradable materials, biodegradable composite materials. So we want to do some chemical conversion, thermochemical conversion of starch to produce those biodegradable polymer materials. So that's the purpose. So here, very briefly, starch is a carbohydrate. It's very important for the food and for the human and animal diets. It's a main constituent for traditional food. Okay, lots of food contains starch, and it's a polymer. So it's similar as cellulose, just a little bit shorter than shorter chain. Okay, so it's easy to digest. So starch, and it can be straight chain or can be branched chain. So that's the starch, natural starch. And why we need to do some research on that? Oh, what's the purpose? So the reason we want to use starch as raw material for biopolymer or biomaterials, because the starch have some of the advantage. We know that starch is very popular, is not very abundant. Okay, and in Canada alone, produce 50 million tons of the starch, grain, not grain, but the majority of the components starch. And it's very pure, high purity. Unlike the synthetic chemicals, has some impurity, but starch is very pure. It's a very pure materials. And it's biodegradable, and the cost is low. Okay, so that's the beauty of the starch. And why we want to produce a biomaterials or biopolymer or the biomaterials from starch? Because biomaterials, we have those of the advantage. Is a biodegradable. It's an environmental benign. Okay, so that's and also inexpensive. So and the market is growing. Particularly in Canada, we look at the bioeconomy. So that's to make this more attractive. So to convert starch to the chemical materials. Okay, so we need to do something. Otherwise, we cannot use starch directly. So the reason is that the starch is a high polarity. Okay, has high polarity, high crystallinity. It's a difficult to process, to melt the process. Okay, and also has a strong intermolecular interaction because of hydrogen bond. So which makes the starch is not that good at a candidate for polymer materials because it's not easy to process. So we need to do some of the modification. So one of the main stream of modification, the technology is to do esterification. So we modify this the starch molecule. We replace the OH, hydroxy, the function group, by an ester. So which make this material easy to process, has a better compatibility with some other polymer, for example, PVC and polypropylene. So those are of the common materials, common polymer materials. So which make this is the technical route. So we need to modify the starch chemically. And after modification, the starch become a starch acetate. Starch acetate have lots of application. So I just highlight here. So some, for example, biodegradable packaging materials, okay, foam and plastic materials, composite, and this is some real example produced from starch. It's a biodegradable the plastic materials. And this is the chemistry. Okay, so we can convert starch to starch acetate by using the starch, by using the acetic anhydride, and based on the catalyst and based on heat. So that's a thermochemical involving catalyst. So we can convert, we can replace, basically we can remove this OH by ester here. And this can make the starch is the kind of polymer. It's easy to be blended, be utilized as the polymer materials. And some of the research have been started very early in 1942. So people already start to produce the starch acetate. But the majority of the process is very common. They use a sodium hydroxide solution and react at a high temperature. And this sodium hydroxide will convert to sodium the acetate after reaction. Sodium acetate is not that expensive material. It's kind of waste material, waste stream. So we need to find an alternative process. We call it a green process. We cannot produce some waste materials and then we can produce some useful materials. So this is kind of the trade-off. So we should look at a more advanced technology. We can produce a starch acetate but minimize the emission of some waste stream. Okay, so many of them, so it still summarizes the existing technology and the performance. Okay, if we look here, so the starch acetate can be there's a degree of the substitute, DS, because starch has 3 OH function group. So if you replace 3, that degree of substitution could be 3. But most likely, most of the process only can replace about 1 and 2, okay, 2.5, not a complete substitution, depending on the conditions. Okay, so just a quick summary. So for the existing process, existing technology, the degree of substitution is normally 1 to 2 or less than 3. Okay, and also large quantity of sodium, the acetate product is produced as a byproduct, as a side product. This material is not that useful, so it's has low market value. And reaction conditions sometimes related to very high temperature, high pressure. So which is not desirable in terms of the energy cost. And the loss of the yield because of this form, because of the hydrolysis, because they use a sodium hydroxide catalyst, and this catalyst can hydrolyze the acetic anhydride, this reactant, so which make this whole process not that high yield. Okay, the efficiency is low. So now we want to propose different. We want to propose a new process that using new catalysts. Okay, so here we have the research done already. So we have starch, we have acetic anhydride the same, but we not using water. We use acetic acid as the reaction medium, because this is also a product. So we do not generate some useless materials, not generate some waste stream, because this acetic acid is a product, and also we use it as a solvent. And then we have different catalysts, and then we can simply through these reactions. The reaction temperature 120 for 2 hours, and we can get the starch converted almost completely. So starch, normally starch, if you dissolve in the water, it's a slurry. But after the reaction is done, it's become a clear solution. It's transparent. So it's disappeared, almost disappeared. We cannot see the color. So it's a transparent solution. That's the product. That's a starch acetate. So we can do the separation, and then we can get a product. And then we have the solvent acetic acid can be recovered. So that's the beauty. So we do not produce some of the byproduct, some of waste stream. And this is the comparison between the raw materials and the product. So that's a starch. That's like a corn starch. We use a corn starch. And this is the starch acetate produced. So we look at this is more like a crystal, or more not a actual crystal. This is like still a solid materials, but this looks more like some sort of material, some plastic materials, not a powder. Okay, so that's the product. And this slide just summarize some perform different catalysts. So because the patent is still under application, so we are not able to get what type of catalyst, but we separate in the group A, B, C. So we can show the difference. So group A, catalyst A actually produce a very high yield. So 80%, 85% yield. So which is very high. And the catalyst has the advantages. This catalyst is less expensive and also can be reused. So after reaction. So that's the catalyst A. Actually, catalyst C is similar, but catalyst C is a little bit more expensive. So we choose catalyst A as more promising catalyst. And we have the other summary, because I don't want to get more details so far here. Okay, so in order to prove that the starch acetate is starch acetate, not a starch. So we have the NMR spectrum here. So that's original starch A. And we look here, this is the function group. Okay, that's the function group of ester. The ester group shown here. So without esterification, no ester group. Very, very, very negligible here. And if you do the esterification, and this BC actually different substitution ratio. This is the 1:2 ratio, 1:3 ratio. So substitution degree of substitution is 3, about 3 and 2. So we can look at here, and we can calculate. This is a proton. This proton is this H. That's the ester on the ester group. And another function group here, shown from here, between this and here, between the 3.5 to 5.5 here. So those are the H proton, because this NMR is H NMR, so it's only look at a proton. The proton here, so this is the proton, is the H2 is here, shown this here. Okay, this is ester group here. And the other proton is on the skeleton of the glucose. So we have H. So total, we can count the total number of H for this 7 in red color, and non-H is on the green color. And we can calculate the percentage by do the integration. So the area under this area, and the area under this spectrum, we integrate, and we can do the ratio. So we can actually calculate ratio. Actually, with the ratio is about 1.4. Actually, slightly higher than a theoretical ratio, which means that all the OH is gone. All the OH, the function was gone, replaced by ester. So this degree of substitution is 3, as expected. So that's the proof of this product. Okay, so second, the research we have done in the past several years is about the how to produce a biophenol by using the biomass. The phenol, we already have some introduction. Phenol is very useful. And this is a global market. So phenol formaldehyde resin. This is adhesive. So this is a kind of the model structure. So we have phenol linked by the methylene group, actually come from formaldehyde. And we can make this is cross-linked the mature polymer material. This material is a curable thermoset. So if you increase the temperature, it becomes solid. And then permanently, we cannot degrade it and we cannot reuse it. Unlike a plastic material, we can reuse it. But this is a thermoset materials. And the market is about 3 million ton, okay, global consumption. And if you look at the North America, the market is about $2.3 billion and $10 billion in the world market, mainly for the house construction, furniture. So those are main applications, but also utilized as the electrical, as an insulator, packaging materials. So that's PF resin, phenylformaldehyde resin. And here, so main application, wood adhesive, and the cost-wise, the price is about $1,500 to $2,000, depend on the the price. Okay, so the applications it can be electrical application, can be wood, engineered wood materials, plywood, OSB, and it can be used as insulation materials in aircraft. Okay, so phenol is the key. So almost the production. So production of the phenol, 35 or 40% of phenol are utilized as in resin in the USA. Okay, similar as in the world. So the global production of phenol is about 10 million tons phenol. And 95 phenol is produced from the petroleum. From this process, we call it cumin process. It's oxidation of the benzene to form a phenol and also produce acetone. So this is a cumin process. So 95% of phenol we need use benzene. The benzene need to derive from petroleum. So which make this process not sustainable because the petroleum consumption, a petroleum reserve, okay? So we need to find an alternative. So that's the driving force, that's the motivation. So petroleum may be run off or may be consumed completely in about less than half century. That's just an expectation, that's the estimation only by shale oil, but actually maybe longer because in Canada we have oil sand. We can sustain a couple more years, particularly in Canada, so we do not have an energy problem. And natural gas, coal, those can be a little bit longer years, but in terms of the benzene production, petroleum is one of the major source. So we need to look at an alternative because the lifetime of petroleum is not that long, okay? So only less than 50 years. Okay, we already know that the lignin is a natural polymer of phenols. So we can utilize a lignin from wood as a phenol feedstock. So which make this research approaches or methodology. So we can liquefy the wood or liquefy lignin to make a phenolic bio-crude oil. Just like petroleum, we make a liquefied lignin or liquefied biomass to make a liquid. And then this liquid contains lots of phenol. And we can replace phenol directly by using this oil. So we can produce the modified oil, and then we can produce some bio-based resin, phenolic resin. Or another approach we think more promising is we separate lignin. Because in the biofuel industry, they do not lack lignin. They want to get rid of lignin, and then they use the cellulose to produce sugar. So we can utilize that lignin. We can get lignin out of biomass, and then we can do depolymerization. We purposely break down the polymer to make a monomer or dimer or some of the other small oligomers. And then we can produce the biophenols. Those biophenols can have higher reactivity. We can get a complete replacement of the phenol in the resin industry. So that's another major application for lignins, to produce bio-based phenol and resin adhesive. And the research, just some typical result for depolymerization, because I said that's more promising. So we can depolymerize lignin. And this lignin comes from pulping industry. So after we produce the paper and some lignin is waste materials. So we can get that lignin, it's alkaline lignin. The molecular weight is very large, it's 10,000 molecular weight. And we can break down those molecular weight, those larger molecule to small molecule to biophenols by the process we call by the depolymerization process. And this is a thermochemical process involving temperature 300 degrees C and involving hydrogen as a reducing agent. So this is reductive depolymerization. And then we can depromize this lignin in different solvent system, including water ethanol mixture, and including 100% ethanol. So we compare the different solvent system, and we can get the performance. So in the water system, it's very simple. Just water and solvent, it's green solvent, because water is not any environmental issue for that. And we can get a depromized lignin, about a 50% yield. But compared to this system, water, ethanol, the coal solvent system, we can look at the difference. So almost double the yield. The yields are close to 90% yields, very high yield. And then the result, the GPC result. GPC is the permission, the chromatograph for the molecular weight determination. So we can determine molecular weight, Mn. Mn for those Na means they're too large. It's still large polymers, so large oligomers. So it's not detectable in the spider equipment. But for this system, we can get the 415, very low compared to the original lignin. 415, if you look at the the monomers, actually it's about a dimer or trimer range. So that's the average. And if you depromize in the ethanol, even the yield is low, but the molecular weight is even low, so 260, almost 1 or 2 range only. So that's the very, very large depromization degree. So which make this products very useful as a biophenol. And then we utilize, we try some catalysts in the system, and some catalysts shown here. For example, we try the different catalysts. Some catalysts can slightly change the yield, but not as significant. But the catalyst performance can reduce the molecular weight further to 400 to 350. So those are the effect of catalysts. So catalyst can further decrease the molecular weight. And then application. So for engineering, we look at the application. So how the biophenol can be utilized. We can produce some resin, and then as an adhesive to bond this plywood, and the plywood can be tested for the strength, the bond strength. And this is a comparison between PF. PF is a pure phenol formaldehyde resin. That's the control. That's the petroleum-based phenol and formaldehyde resin. That's the commercial resin. And then this is the bio-based resin. 50% DLPF means depromized lignin-based phenol formaldehyde resin. Replacement 50% of phenol by using this bio-based phenol. And 75% DLPF is a 75% replacement. So in terms of green feedstock, green component, is 75% components is green based. So the dry strengths and the wet strengths, both of them actually is better than the control, which means that the natural polymer, natural based adhesive is strong, bond strong, the material, bond wood, even stronger than the petroleum based, the resin and the adhesive, which gave the industry, actually the industry is really interested in this result, and some of the commercialization is down the road. So we can look at the actual producer. We even test 100% DLPF. The bond strength is still not bad. So which means that, so for the petroleum, for the resin, petroleum, we can get rid of petroleum totally. And recently we have another research. We can replace the formaldehyde. We know formaldehyde is not a good compound. It's a carcinogenic compound, causes cancer. So we do not like formaldehyde. So now we are now looking at, we have the research to replace the formaldehyde by using sugar, by using a natural aldehyde. So that's another research to get the 100% green-based adhesive. So which is another potential for this bio-based chemical and materials. Final the example of research for bioproducts, the conversion. So one-step catalytic conversion of the ethanol into butanol and hexanol. So this is more related to the fuel and the chemicals from the platform chemical. Ethanol can be a platform chemicals. They can be from corn, can be from wood, from agricultural residue, as I said before. So the motivation. So any researcher, we need to answer why we want to do it. Is it worthwhile to do it, or is there any alternative, better way to do it? So this is the motivation. So ethanol, we know ethanol as a fuel is not new. So we are now using the daily base. We get a gas station and then 10% alcohol already in your gasoline. So that's the ethanol fuel. But ethanol fuel has some problem because ethanol is low heating value. It's only 20 megajoule per liter compared to gasoline 32. So very low. Okay, if you blend too much ethanol, then the gasoline, the one tank of gasoline cannot drive as expected long distance. For example, you want to drive 500 kilometers, and if you blend too much ethanol, then you cannot drive that long because the heating value is low. Okay, and also ethanol has another problem for high vapor pressure, and also ethanol can absorb moisture in air. So if you leave that tank of gasoline for a longer time, then you have lots of water in your tank because ethanol absorbs water easily. So which make the ethanol is not a best solution for fuel. Now we look at butanol. Butanol is much better because butanol, the heating value is closer to the gasoline. And the butanol vapor pressure is low. So where is look here, so heating vapor pressure. So butanol actually is more closer to this gasoline. And also not affected the octane number too much. Butanol has still high octane number, but okay, so in the range of gasoline. So that's the butanol. Okay, so butanol, just a brief here. So butanol has 4 carbons. Okay, so it's a long chain. It's a higher rank the alcohols. It can be an intermediate, not only for fuel, can be chemical. So lots of the polymer industry, they use butanol as an intermediate. For example, we can produce isobutyl acetate. We can produce some polymers. Okay, and also rubber materials. And it can be a very important solvent in the paint industry. So we can use butanol as a solvent. And also as a potential fuel to substitute gasoline completely. We can use 100% of butanol in a gas tank because butanol is very close to the gasoline. It's very good capability with the gasoline. Okay, so U.S. started to look at butanol. So U.S. predict that. So 2020, 57 billion liters of butanol will be produced. So they start to look at butanol now already. So to promote the butanol industry. Okay, so the butanol versus the ethanol, we already know some of the idea already. So butanol has a higher heating value. Butanol is safer because vapor pressure. Okay, so butanol has a much higher capability with the gasoline. Okay, butanol can be blended with gasoline easily to up to 100%. Unlike gasoline, if you blend too much, then this become two-phase separation because it's not soluble in the gasoline. Ethanol, butanol is different. And butanol is clean because it does not contain any sulfur, nitrogen. So those make butanol as clean fuel. And butanol is much more valuable than ethanol. If you look at the price only, for ethanol the price is about the 700, but butanol price is doubled. Butanol is for 1400 or 1500. So that's the economical value of butanol. It's more expensive. Okay, so in terms of synthesis, chemistry industry. So industry, butanol is synthesized through this process. This octosynthesis. Actually, synthesis from the petroleum-based materials. It's from the propylene gas. And then we can do oxidation and reduction. Finally, we can get the butanol through this aldehyde intermediate. And by using catalysts. And there is another process, rapid synthesis, another one-step process. So we can start a propylene gas and the different catalysts. We can produce the butanol. It's a butanol and also the isobutanol. It's normal butanol, isobutanol. So that's the industrial process to produce butanol. So alternative, we can produce butanol by the bio process. This is the ABE process. The acetone, butanol, and the ethanol process is very popular. It's developed a very long time ago, in 1861. Okay, and also it's very popular from World War II. This uses some particular bacterial stream, okay, to produce from sugar to the butanol. But the problem for this ABE process, I summarize here, some problem. The ABE product actually is toxic to the bacteria because you produce acetone and produce butanol. Those are organic chemicals. Actually, those chemicals are poison to the bacteria. So, which make this a problem. So, which make the low production, the concentration. We cannot get a high concentration. the fermentation in the process. So only about 2%. And also in terms of the productivity, it's about 4.5 gram liter per hour. So it's limited, the production rate. And the low yield, because of this toxic issue. So the yield is only about 25 gram, 100 per 100 gram of glucose. Compare that to ethanol. Ethanol, the yield is higher. Because ethanol, you can get a 50 gram per 100 gram of glucose. So if you produce ethanol, then you can get a high yield. But how to make the ethanol to butanol? That's the motivation. So we can convert ethanol to butanol. So first, look at the butanol, the demand. So butanol, in 2015, we had lots of demand in butanol, in particular for fuel, biobutanol as next generation fuels. And the market, 250 billion biofuel, the market on that, on the butanol. So which make the butanol more profitable, or the more demand, larger demand in about 10 years from here. Okay, so the research objective. So we want to try something simple. So we want to produce the butanol from ethanol by the simple reaction, by one-step reaction. Condensation. Condense two ethanol to one butanol. We remove one molar of water. And this is a simple chemistry. So we have this is the conversion. So 1 kilogram of the ethanol, the theoretical can get 0.8 kilogram of butanol, and then 0.2 kilogram of water. So if you can make this process can be achievable and economically or low energy cost, then the butanol production can solve the problem. Because we do not need to worry about the bacteria, the toxic issue, or the yield, the low reaction rate, because this reaction is a thermochemical catalytic reaction. It's a very fast reaction. So, but the point of whether we can get the right condition and right catalyst for this reaction. So we try this, and we achieved some success we can show here. So this is the process we develop for this conversion. This is a continuous process. And this is under pressure. So this is a high pressure reactor, continuous reactor. We have feedstock, which is ethanol, pump it through the pump. And then we pass through here this reactor. This reactor is a packed bed, so we have a catalyst bed inside the reactor. And heated to a high temperature, actually depends on the catalyst performance. And then we can separate. We can control the temperature by here. And then the gas-liquid separation, we can collect the product, and the gas will be removed or can be collected. So here is the performance. So we have three type of catalysts tested here. And the butanol yield, the butanol, and this is the conversion, and this is the selectivity. So the butanol yields the best catalyst, this catalyst get about more than 20% of yield. And then conversion, 35% conversion. Selectivity at 62. And the second catalyst, the selectivity is even better, a little bit better, 63. But the conversion is a little bit low, and the yield is low. So, but this shows some of the promise, because we get this high selectivity. This high selectivity is only for butanol, but also we produce some byproduct, side product. For example, 1-hexanol is one major side product, even more valuable. So, and also some other materials, other chemical in the side product can be utilized as the fuel, biofuel, not a waste materials. So this make this process summarized here. So this can be a good promising the process here. Look at the economic value. So which we take this as example. 1 ton of biomass, cellulosic biomass. This can be, if you look at some biomass, the cost, we assume the cost, the $50 per ton. Okay, assume this is a waste material from agriculture. So $50 per ton. And we do the fermentation first. We convert that to ethanol first. So we can produce, in 1 ton of the biomass, can produce 180 kilogram of the bioethanol. And the bioethanol, assume bioethanol is the price of $700 per ton. So this can give you $126. So the dollar value is doubled, which gives some of the economy. And if you produce bioethanol, we can make the money, because this end product is much more expensive than the feedstock. But we cannot just stop here, because ethanol we can use it as only 15% in the gasoline. And ethanol has lots of problems. We already mentioned that. So we want to further convert the ethanol to butanol. So by using this process, using catalyst, using the conversion temperature 200, 300 degrees C, and we converted the butanol from ethanol. They assume 75% selectivity. We got a 62%. That's not enough. We need to do more research on that to improve the catalyst performance. But 75 is achievable. So if you assume 75% selectivity, then we can get 108 kilogram of butanol. The price, if you look at here, is 1,500 or 1,400 per ton. It's about 162. Then some side product, including the hexanol, including some other side product, which can be used as a fuel. As a fuel, assume 1,000 per ton for fuel for this side product. And then the total value is $200. $200 end product compared to feedstock $50, compared to $100 for the ethanol. So this is the further the profit, make a profit doubled. So if you make this process more consume less energies, so we can make this process more profitable if you convert to the butanol. So that's the scenario we build for the future development. Okay, so finally, so that just acknowledge some of my colleagues, my collaborators. So my research collaborator in my former university, Lakehead University in Thunder Bay, and also we have several collaborators, for example, from visiting professors from Iran, from Netherlands, and that's in my group. And also postdoc fellow and the graduate student. Actually, they are all involved in several projects involved in today's topic. So I appreciate that. And also that's the group pictures that we took in last summer, and some funding support this research, and my own Western University to provide the opportunity for the position. Thank you so much for your attention, and any question I'd like to discuss with you.
Any questions?
I have a few.
Yeah.
If you go over your slide from the end to...
Yeah, sure.
Yeah, for last slide, the cost, yeah, this one.
Yeah.
It's starting from $50 and then you get the value 200 at the end, right?
Yeah, we did not consider the consumption.
Yeah.
The energy cost, yeah, we did not consider. Just a simple, this it's a margin only. It's any product margin. But if you subtract for example, the cost of fermentation, cost of hydrolysis, altogether, maybe the profit is minimal, but still profitable. Otherwise, some other company, they're still looking at that.
Okay, thanks. And the other one is for your butanol, when you produce it, it's mixture with some other one. How do you separate them?
For separation, we do separation by distillation. But for the industry application, maybe we can look at other better separation. Yeah, for now, in the lab, we do the simple distillation. We can get the butanol because the boiling point are different.
The last one is the introduction. You mentioned the products. I think it said the bioproduct market outlook.
Yeah.
You mentioned the carbon fiber, the glass fiber produced from bioproducts. So I'm wondering, how can you produce glass fiber from the bioproduct?
The glass fiber not. Yeah, probably that's the mistake in my. Maybe I can. Glass fiber is not from biomass. Yeah, but a carbon fiber definitely. Yeah.
Yeah, I saw you have both.
Yeah. Yeah, that's a good point. Maybe some typo error there.
Yeah, this one.
Glass fiber market. Yeah, glass fiber market. That's actually is the replacement of glass fiber using the carbon-based fiber. That's the market. Yeah. But it showed that 60% from renewable. Maybe 63% of glass fiber from renewable from plants, because some of them produce from ash, say, from a power plant ash, from coal-fired ash. The silica they can utilize that produce a glass fiber. Yeah.
So the carbon fiber you kind of like using lignin and do carbonization to produce.
Yeah. We have a group, actually, there's a research, actually, it's a strategic research network. I'm a part of that. So we have a research group in UBC, John Cadler's group, and he's look at how to produce the carbon fiber from lignin. Yeah.
Okay, thank you. Very impressive.
My pleasure. Thank you for your question.
Any other questions?
I have one question about lignin.
Yeah, sure.
You from lignin you ended at the phenol.
Yeah.
From the phenol you can make chemicals. Can you make a fuel from phenol?
Yeah. Yeah, definitely. We can upgrade the phenol to the fuel as a fuel additive, as a diesel fuel.
Okay.
Yeah, by hydrotreating.
Okay.
By adding hydrogen, we can produce benzene by cyclic hexane, so we can make a fuel, biofuel.
Is it commercially available now?
Not commercially, still in the research stage. There's several groups in the U.S., particularly in some of the university, particularly, for example, in the Wisconsin University, they do the hydro, and also in the research lab in U.S. renewable research lab, they do the hydrotreating. Yeah.
I have
Yeah.
a question around the starch acetate.
Yeah.
Could you just flip over to
Sure.
one of the slides? My chemistry isn't fabulous.
Here.
And I was just trying to count the carbons.
Yeah.
Is the acetic anhydride substituting carbons?
No, it is substitute only OH.
It just takes the OH?
Yeah, take OH.
Okay.
Just to make this hydrophilic to more hydrophobic,
Yes.
and make this more compatible to the other polymer.
Okay, and then it's just a question of the efficiency of how many of the three you're taking.
Yeah, that's just this three, 1, 2, 3. That's OH.
Yeah.
That's the hydrophilic OH.
But are you adding, you're in the upper right, you've got a COCH.
Acetic acid is a byproduct, it's side product.
Above that.
Yeah, from here.
Above that.
About here,
COCH
COCH3 is the ester.
is added.
Is added on this.
Is added on there.
Yeah, yeah. It's
So
an
you're
ester.
adding that ester.
Yeah, exactly. So that's the esterification reaction.
Right. But where does the ester come from? It comes from the acetic anhydride.
No, from acetic anhydride. Yeah.
And where does that come from?
This acetic anhydride
How is that
actually
made?
it's made from acetic acid actually.
It's made from acetic acid.
Yeah,
So
but
it can also be bio-based
yeah, it can be bio-based.
or petroleum-based.
Exactly. Yeah.
So in order to keep it bio-based, you want to be able to source your acetic acid from a bio-based.
From
So
fermentation.
you have
Yeah.
to look at that
Yeah.
sequence to get
Exactly.
that feedstock.
Yes.
into the system.
Mm-hmm.
Okay.
Yeah.
All right. If no other questions, I want to thank you all for coming to this seminar. Appreciate that. Also thank Wise for the staff for arranging all this. Okay. Thank you very much. I hope you have a wonderful evening. And feel free to talk to him.
Yeah. Thank you.